This is problem number 2, chapter 8, page 257. So this is a real simple one since it's right at the beginning of the chapter. According to the manual, a certain car, a maximum torque of magnitude 65 Newton meters should be applied when tightening the lug nuts on the vehicle. If you use a wrench of length 0.330 meters and you apply the force at the end of the wrench at an angle of 75 degrees with respect to the line going from the lug nut through the end of the handle, what is the magnitude of the maximum force you can exert on the handle without exceeding the recommendations? So let's draw what we have here. So we have a lug nut. If I've got a hexagonal thing here. Okay, we got actually got a little nut here. And so we're going to apply a force to this. So we've got a wrench, and the wrench says, okay, let's read what it says. If you use a wrench of length, so the radius of this from the wrench, from the lug nut to the head of the wrench is 0.330 meters, which is about a foot, a little bit more than a foot long. And then you apply this force, and it says, let's read it. You apply the force at the end of the wrench, which is right here, at an angle of 75 degrees with respect to a line going from the lug nut through the end of the handle. So what that line they're talking about there is if you extended this line like that. So it's a line going through here, through the end of the lug nut. And so the angle between the force, so now we have a force that's acting on here somewhere or another. So let's just draw it like this. So the angle between the force and the line drawn is 75 degrees. So that's the 75 degrees. So what we're looking for is, let's put an F on here, and it says the torque, the maximum torque is equal to 65.0 Newton meters. And the torque is the component of the force that is perpendicular to the radius times the radius. The other way is you can take this force and find the radius that is associated with a perpendicular to this. If you were to extend this force out in its direction, so this goes like that, and then you look at the radius from here to that point where this is a perpendicular, then you would take that distance times that force, or you can take this distance times that force, and it comes out to be the same answer. So we're only going to do it the one way. We're going to break the force up into two components, one that's pushing in on the lug nut, which is not going to create a torque, and one that's perpendicular to it, which is going to create a torque. So this force here can be broken up into two components, one that's in the direction of the radius, one that's perpendicular to the radius. And so it's just a geometry problem after this point. If this is 75 degrees, then this is going to be 15 degrees. And we're looking for this part of the force, which is the adjacent side to this angle. So we'll call this F sub t for tangent. So F sub t is going to be equal to F times the cosine of 15 degrees. And it's 15 because this is a right angle. And then, so the torque is going to be equal to the product of the tangential force times the radius. And we know this is maximum 65, so we can solve for the, and let's just go ahead and plug it in here. The tangential force is the force times the cosine of 15 degrees, and then we multiply by the radius, so this is that times the radius, and so we can solve for the force. The force is equal to the torque divided by the cosine of 15 degrees times the radius. So now we have to just plug in. Force is equal to 65.0 Newton meters divided by the cosine of 15 degrees times the radius, which is 0.330 meters. And you see from a unit standpoint, this is unitless. We have Newton meters divided by meters gives us newtons. So that makes sense. And the larger this angle is, the more that you're actually going to be pushing towards the lug nut and not creating a torque. So if we were perpendicular, if our force was pushing perpendicular to this radius, then the total force would go into creating a torque. So we have 65 divided by the cosine of 15 divided by 0.33. And we see that the force is going to be equal to 204 newtons. So that's the maximum force that can be applied here. If we take 204 times the cosine of 15 degrees, that'll give us a tangential force. So let's just calculate that. They didn't ask for it. But the tangential force would be 204 newtons times the cosine of 15 degrees. So that's 197 newtons. So we have 197 newtons acting in this way. And if we took 204 times the sine of 15 degrees, that would give us the part that's being pushed directly into the handle, straight down the handle. So this force acting through a distance of 0.330 meters, so that would be the torque, force times distance, is times 0.330. We get 65 newton meters, which is the torque, the maximum torque this can apply. I mean, that this can withstand. This is problem number 9, page 257. And it says a cook holds a 3-kilogram carton of milk at arm's length. What force F sub B must be exerted by the bicep muscle? Ignore the weight of the forearm. So let's try to draw a sketch of this. What's going on? You have the forearm like this, and then we have a force on the forearm in this direction, and the angle is 75 degrees between that and the vertical. So if we draw a vertical line, we have 75 degrees. This is F sub B. And we actually have a point of rotation. The actual rotation is around this point. So let's extend this forearm a little bit. So there's the forearm extended. So the bicep's hanging there, and that's the elbow. And so the distance between there and the elbow is 8 centimeters, and the distance from here to here is 25 centimeters. This is 25. This is 8 centimeters. And the force at the end, which is the weight of the carton of milk, is right there. So this is, they call it F sub G, which I'm assuming probably means the force due to gravity. They're showing it as a vector. And they say that the mass of the milk carton is 2 kilograms. So we know that F sub G, which is the weight of the milk carton, is just mass times acceleration due to gravity. So we have 2 kilograms times acceleration due to gravity, which is 9.8 meters per second squared. So that's going to be 19.6 newtons. Okay, now what we're going to do is we're going to sum the torques around the elbow, because there are forces on the elbow, but we don't really need to know that to solve the problem. So it would actually be an X and Y force on the elbow. So if we're going to sum the torques around this, we're going to have two forces. We're going to have one force that's going to want to tend to rotate counterclockwise, and we've got another force that is going to cause it to go clockwise. So what we can do is we can create a force perpendicular to the radius and one that's parallel to the radius. So we have an X component. Let's call this X. We'll call this Y. So this will be F sub B Y, and this will be F sub B X. And the one pointing in the X direction is really pointing right here. So this one goes right through the radius. So therefore, there's no torque associated with that force. So let's bring that down here. There is a torque associated with this radius, and once we do the geometry, then we'll be all set. So what we can say is that the force due to the muscle B in the y direction, so this is going to be the adjacent side to this angle. So it's going to be equal to F sub B times the cosine of 75 degrees. This force, which goes right through the elbow, is going to be equal to F sub B times the sine of 75 degrees. Okay, so this is one force and this other force, and they're both now perpendicular. So all we have to do is sum the torques around the elbow. So the sum of the torques, and because we're in equilibrium, let's call it E for the elbow. Because we're in equilibrium, the sum of the torques have to be equal to 0. So we have this torque, which is this force, times the distance, which would be 25 plus 30. So we have the total distance. So we have the force, which I'll just put in as F sub G times 25 plus 8, 33 centimeters. And I'm using plus because it's going to rotate counterclockwise. And then we have, going the other direction, we have F sub B Y, the magnitude of that force, times the radius from the elbow to the muscle, which is going to be 8 centimeters. And those have to equal 0. Well, F sub BY, so let's put this in, F sub G times 33 centimeters. And again, I'm going to leave it in centimeters because if everything is in centimeters, it'll work out, they'll cancel out. So we have negative F sub BY is just F sub B times the cosine of 75 degrees times 8 centimeters. And that's equal to 0. So we can solve for F sub B. F sub B is going to be F sub G times 33 divided by these two terms, which are multiplied by F sub B. So to get F sub B by itself, we're going to divide both by those two. Cosine of 75 degrees times 8 centimeters. The negative sign, when we move this to the right-hand side, it'll become positive. Oh, pardon me, when we move this to the right-hand side, it'll become negative, and then the two negatives will cancel out. So the final answer is going to be F sub G, which was 19.6 newtons. That was the weight of 2 kilograms, times 33 divided by the cosine of 75 degrees divided by 8. So what do we get? We get 19.6 times 33 divided by the cosine of 75 divided by 8. So we get 3 112 newtons. So that's the force FB, and it's much larger because you've got this lever arm that's causing this extra torque. So the longer the person's arm is, the more this torque would be, and the stronger the muscle would have to be to provide this force. This is problem 19 in chapter 8, page 259. So what we have is we have a sign hanging from a wall, and it says, let's just read it, a 500 Newton uniform rectangular sign, 4 meters wide and 3 meters high, is suspended from a horizontal 6 meter long uniform 100 Newton rod as indicated in the figure. The left end of the rod is supported by a hinge, and the right end is supported by a thin cable, making a 30-degree angle with the vertical. Find the tension T in the cable and find the horizontal and vertical components of the first force exerted on the left end of the rod by the hinge. So I'm going to draw a figure which represents what this problem has, and you can look at the drawing in the book. But we have a beam which is 6 meters long, and we have a cable which holds this thing up. And so we have that. Let's put a wall just to have something to hold it against. So there's your wall. Okay. And then we have a sign. Now the sign is hanging, it says it's 4 meters wide and hangs from the end. And so if this is 6 meters long and the sign is 4 meters long, then you're going to have 2 meters between here and here, and we're going to assume that all of the mass is supported, all the mass for the sign is concentrated at the middle. So what that will mean is we have a force that's pulling down right here. This is the weight of the sign, and the center of the sign is going to be 4 meters from the left end. Okay, so that's because the sign is 4 meters long from this end. So we get 2 meters plus half of 4 is 2, which, so 2 plus 2 is 4. So that is, let's see, what's the weight of the sign? 500 newtons. Then we have the rod, which is supporting the sign. And because it's a uniform rod, all of the weight of the rod is going to be concentrated, can be assumed to be concentrated at the center of the rod, which is 6 meters. This rod is 6 meters long, so this is going to be at 3 meters. So we have 100 Newton force acting here, and the distance from the wall is half of 6 meters, which is 3 meters. Okay, so we have the sign, which is 6 meters. So let me put that on here. So this total distance all the way to the end is 6 meters. And that's where the tension is being applied. So we have this cable which is being in tension because as this thing pulls down, it's going to create this, it's going to stretch the cable, it's going to put it in tension. Now the angle here is 30 degrees, and because this is a 90-degree triangle, we have a 90-degree angle right here, and we know that this angle is going to be 60 degrees. Since the sum of the angles inside of a triangle are equal to 180. So if this is 90 and this is 30, then it has to be 60. So we're going to simplify this a little bit, so I'm going to put another page on just so we can kind of clean it up a little bit. So I'm going to show this as being my rod. And then we're going to have forces. I'm going to show the forces in red. So we have the tension pointing in this direction. So this is going to be T. This is going to be 60 degrees. We have the weight of the sign pulling down right here. We have the weight of the rod pulling down right there. And we're also going to have a force that's going to be acting in this direction to support that end of the rod. So we're going to call this force F. And we have to put some dimensions on it, like over here. So the same kind of deal. This is going to be 3 meters. This distance will be 4 meters. And the total distance will be 6 meters. So the distance to the, I'm going to show it right here, the distance goes all the way up to here. To the end is 6 meters. And what we can do finally is we can break the tension up into two components. We have a Y component of the tension, and I'm going to put it down here. We have an X component of the tension. So we're going to call this T sub Y, and we'll call this T sub X. And likewise with the other force that we have on the other end, we have F sub X and F sub Y. And the sum of these two vectors, the F sub X and F sub Y, will be the total force. So if I take this up here and I add the two vectors, I get the total vector. That's how vectors work. So we're going to call this F sub X and F sub Y. And this is F as the resultant vector. Okay, so that's everything we need on this problem. And we're going to use the sum of the torques around some point is equal to 0 because it's in equilibrium. We've got the sum of the forces in the X direction have to equal 0. And the sum of the forces in the Y direction equals 0. So those are our three equations. We're going to have three unknowns. We have the two components of this force, and we have two components of this force, but we know the angle between them, so that reduces the number of unknowns. And we forgot, or I forgot, these two. This is 100 newtons. This is 500 newtons. So in these kind of problems, the best thing to do is to do the sum of the torques first. And we're going to sum the torques around this point. And the reason we do that is so that this force has 0 moment arm, and so this drops out of this equation. And the only unknown we have is the tension. Now, when we do torques, we always want to use the component of force that is perpendicular to the radius. So our radius is this beam. So you can see this one's already perpendicular and this one's perpendicular. This one is not perpendicular, so we break it up into two components. So the one T sub X is not perpendicular. It goes right through there, so there's no moment arm. And this one is perpendicular, so we use this total distance for the torques. So let's sum the torques about the left-hand support. And we know those are going to equal 0 because it's in equilibrium. So we take this force. Let's just start from the left-hand side. This one's 0 because there's no moment arm. We have this one, which is 100 newtons. Torque is force times distance. 100 newtons times 3 meters. And we look at the sign by looking at the direction this rotation would occur. So here, for supporting here, if we had a hinge here and we push down, it's going to rotate clockwise, which is negative. The second element will be 500 newtons times 4 meters, which is the distance. And again, it's negative because this would cause a clockwise rotation. And then we've got one more, which is T sub Y. So we have T sub Y, which is a force, that's tension in the cable, times the distance, which is 6 meters. And it's plus because this tension would cause a counterclockwise rotation, which we consider to be positive. So you can see we only have one unknown. What we find out is T sub Y is equal to 100. I'm going to leave the units off here. 100 newtons times 3 meters plus 500 newtons times 4 meters divided by, we'll divide by them by 6 meters. So if we get my calculator out, (100 times 3 plus 500 times 4), That's 2,300, and we divide by 6. So that is 383 newtons. So that's T sub y. Now, as far as finding T sub x, we can do that just from geometry. So let's just draw the tension. Actually, it goes that way. Make it a little bit longer. So that's our total tension. We just calculated T sub y, which was this vertical component. And then we have T sub x, which is this part. So we have this right triangle because we're dealing with vectors. So let's write that in here. This is T sub x, this is T sub y, this is T. This angle is 60 degrees, so this angle would be 30 degrees. Or you could say this one's 60 degrees, either way. So if we just use the definition of the cosine, we know that the cosine of 30 degrees is equal to the length of the adjacent side divided by the length of the hypotenuse. We also know that the sine of 30 degrees is the length of the opposite side divided by the, let me just fix that because it doesn't look like a y, it looks like an x, so that's T sub y. So you can see what we can do is we can use either one of the, well, we know T sub y, so we're going to use this one. So we can say that the tension is equal to T sub y divided by the cosine of 30 degrees. T sub y is 383 newtons divided by the cosine of 30 degrees. 383 divided by the cosine of 30. And I get 442 newtons. So the next thing we're going to do is we have to do the sum of the forces in the other direction. So we figured out T, the tension. So if we sum the forces in the x direction, again, because it's in equilibrium, it's equal to 0. And really we only have two forces in the x direction. We have F sub x and we have T sub x. F sub x is going in the positive x direction. T sub x is going in the negative x direction. So that's equal to 0. So what we can see is that F sub x, which is another one of our unknowns, is equal to T sub x. And so it is equal to, actually we haven't calculated that yet. So T sub x using this result is the same as T times the sine of 30 degrees. So F sub x is T, the tension, 442 newtons times the sine of 30 degrees. And we get 221. Sine of 30 degrees is a half, so. Okay, so that's F sub x, and then we can calculate F sub y using the sum of the forces in the y direction. So we got the sum of the forces in the y direction. In this case, it's also equal to 0 because we're in equilibrium. And what we have is we have F sub y, which is positive. In the negative y direction, we have the weight of the rod. We have the, let me put newtons on there. We have the weight of the sine. And we have T sub y, which is the tension in the y direction. And these are both pointing upward. So we can solve for F sub y. F sub y is going to be equal to, if you add these two, you get negative 600. And when you move it to the right-hand side, it becomes positive 600. And then we subtract T sub y. So F sub y is equal to 600 newtons minus F sub y, which we just is 383 newtons from over here 383 newtons. And we get 217 newtons. So that's F sub y. We just calculated F sub x down here on the previous page. And you can see they're pretty close to each other, so it's going to be close to a 45-degree angle. And they said, so we found the tension, and it says find the horizontal and vertical components of the force. So we've actually solved the problem as they asked for, but we're going to work one extra step here. We're going to calculate the magnitude of F and its direction. So if we draw this triangle, so we have a right triangle. This would be our angle, theta. And so F sub y is equal to 217 newtons. F sub x is equal to 221 newtons. And so the magnitude of F, so this is a vector. We'll say the magnitude of the vector. We actually use two vertical lines to show magnitude. It is just the square root of the sum of the squares of the components. So we have 221 newtons squared plus 217 newtons squared. 221 squared plus 217 squared. Take the square root. We get 309. So F, the magnitude of vector F, is, we'll round off to 310 newtons. And then the angle, theta, is just going to be the inverse tangent of the y component, which is 217, divided by the x component, which is 221. And as I said earlier, it's going to be very close to 45 degrees because the cosine of 45 is 1. So we get 44.5 degrees for the direction. So those are the correct answers, and just going to go back and we're going to review what we did here. So we made a drawing with all the geometry information. The center of the sign was 4 meters from the wall. The rod is 6 meters long, so the force associated with the weight of the rod is in the middle, which is at 3 meters. And it's 6 meters from the wall to the tension. So we drew a picture which showed all these forces and directions. 100 newtons in the middle, 500 newtons at 4 meters. The end of the rod was at 6 meters. This tension is pointing at an angle of 60 degrees from the geometry of the sign. This was 30, this is 90, so that's 60. And we have a support force on the left-hand side, F sub x and F sub y. So we use these three equations, sum of the torques, sum of the forces, sum of the forces in the different directions. And we always start with the sum of the torques because by choosing this as our point of rotation, we're able to get rid of F as far as in the calculation of the torque. And the only unknown is going to be the tension. We use the perpendicular component, which is T sub y, in calculating the torque. This one doesn't contribute to the torque, the one that's parallel to the radius of the sign. So we have 3 torques. This one, which is 100 times 3, negative because it's counterclockwise, it's clockwise. This is 500 times 4 meters, which is clockwise, so it's negative. And we have T sub y times 6 meters, which is positive because it's counterclockwise. So that's the equation. You solve for T sub y, plug the numbers in, you get T sub y. Then we use geometry, knowing the angle between T and the vertical and horizontal directions. We can draw a vector diagram where we say T sub y plus T sub x is T as far as a vector addition. And we can then just use right triangle geometry to relate T sub y and T sub x and T associated with the sine and cosine and sine of the angle. So you can solve for T from this equation by multiplying both sides by t and dividing both sides by the cosine of 30. And we find out the tension is 442, which should be bigger because this is the hypotenuse, and this is only one leg of it. So that gives us the tension. That was part A. Then we have to use the sum of the forces in the x and the y direction to get the other unknowns, which are f sub x and f sub y. So we use the sum of the forces in the x direction, equaling 0 because of equilibrium, to solve for f sub x. It's equal to t sub x. Those are the only two forces acting in the x direction. T sub x is just t times the sine of 30 degrees from up here. Plug them in, you get f sub x is 221 newtons. And to find t sub y, we need to use the sum of the forces in the y direction. Again, it's equal to 0 because it's an equilibrium. F sub y is, we're going to assume positive. If it comes out to be positive, then we assume correctly. We know t sub y is pointing upward, and these are both pointing negative in the y direction. So we can solve for f sub y, 600 newtons minus t sub y. Once we move these to the right-hand side of the equation, plug in t sub y, which we have earlier from an earlier part of the problem, and you find out f sub y is 217 newtons, which is the two answers for section 2. We went a little bit further just to find the magnitude of the force F. It's just the vector sum of the f sub x and f sub y. To find the magnitude of this side, it's just a Pythagorean theorem problem because it's a right triangle. So we take this squared plus that squared, take the square root, that'll give us this side. We find out the magnitude of F is 310 newtons. And then the angle between the vector, force vector, and the horizontal axis is theta. And so we just use the tangent of theta is this divided by that. Therefore, theta is the inverse tangent of the change in this height divided by the change in the width. As far as the triangle is concerned, we get 44.5 degrees. Okay, this is problem number 20 on page 259. A little bit easier than 19. As you can see, it's in black as far as the color is concerned. So that means it's one of the easier ones according to this guy. So what we have is, it says we have window washers standing on a scaffold supported by a vertical rope on each end. So let's draw a scaffold. A scaffold is just like a flat board that's got ropes on each end. So we're going to show this as a rope on one end and a rope on the other. And if the guy was standing right in the middle there, the forces would be equal, but that's not what happens. So the scaffold has dimensions of 3 meters, so the total distance, so let's do that here, the total distance is 3 meters. And it says it weighs 200 newtons, so let's put a force, let's just show it coming down like this. So this is the weight of the scaffold, and we're saying it's right in the middle because it's a uniform scaffold. So we have 200 newtons acting there. And it says, what is the tension in each rope when the 900 Newton worker stands 1 meter from one end? So it doesn't say which end, but we'll assume it's the left end. So I probably should make this longer. I should probably make this even shorter if I do this kind of to scale. So this is 200 newtons. And then you have the other guy, 700 newtons. And the distance from one end is 1 meter. So this is the distance, 1 meter. Actually, let me move it over a little bit because it's 3 meters long. So let's put it about a third of the way over, reasonably to scale. Okay, so that's 1 meter, 700 newtons. We've got this guy in the middle. Let's make sure I got this all right. Okay, so if we look at the distance from the left end to the middle, that's going to be 1.5 meters, one half of 3 meters. And what we're trying to figure out is what is the tension in the rope. So we'll call this T1 and we'll call this T2. And as you can imagine, T1 should be greater than T2, because if this 700 Newton force were in the middle, you get a total force downward of 900 newtons, and it would be evenly spaced, separated between the two sides. But because this guy is to the left-hand side, then it's going to have more tension on this rope than on this rope. And how do we find that? Well, in this case, there are no forces in the x direction, so this is just sum of the torques equals 0, and the sum of the forces in the y direction equals 0. So our two equations that apply in equilibrium situations are the sum of the torques equals 0, and the sum of the forces in the y direction equals 0. So all we're going to do is we have to choose some point to rotate around. We're going to choose this point. That will allow us to calculate T2 directly from this equation, and then we can calculate T1 from this equation. So again, looking at how we're setting this up, this is our point of rotation. This would be the radius for the first force. This would be the radius to the second force, and then we have the total distance, the radius to the third force. These are going to cause clockwise rotations, which are going to be negative. This one would cause counterclockwise rotation. So the sum of the torques around, let's call this point 0, around 0 is equal to 0 because it's equilibrium. And so we'll have negative from the clockwise torques, 700 newtons times 1 meter minus 200 newtons times 1.5 meters. So those are those two forces. Plus, because of a counterclockwise torque, T2 times 3 meters. So we can solve this for T2. T2 is just going to be equal to 700 newtons times 1 meter plus 200 newtons times 1.5 meters divided by 3 meters. So let's add, to do that, 700 plus 200 times 1.5. So that's 1,000. 1,000 divided by 3 is 333. So we get 333.3333, etc. newtons. So we're just going to round it off to 333. So that's this tension. And then we use the sum of the forces in the y direction to find the other tension. Again, because we're in equilibrium, the sum of the forces equals 0. If it wasn't 0, we'd be rotating. So it's 0 because we're not rotating, we're moving up and down. So what do we have? We have these two forces that are acting up and these two forces that are acting down. So we'd have T1, positive T1 plus positive T2 minus 700 newtons minus 200 newtons. So we already know T2, so let's solve for T1. So T1, you'd have 700 and 200 is 900. It'd be negative 900, but when we move those to the right-hand side, it'll become positive 900. And then we subtract T2 off to get this on the right-hand side of the equation. So now we just plug numbers in. So we have 900 newtons minus 333 newtons. And so we get 567 newtons. So this plus that is equal to 900. This is problem number 33, chapter 8. So get your book out, and I'm going to read the problem, and then we'll kind of draw a figure as we go along. This is a large grinding wheel in the shape of a solid cylinder of a certain radius. So let's draw our cylinder. So this is the edge view, and it has a radius of a certain amount. So we draw the radius in, and the radius is equal to 0.330 meters. It's free to rotate on a frictionless vertical axle, so it's going to be rotating rotating on an axle that's going into the page. And frictionless just means there's nothing to slow it down. So if we apply a torque to this, it'll start speeding up until we let go of the torque, and then it'll stay at that value. Okay, so a constant tangential force of 200 newtons. So let's put a force on the edge of this thing. Tangential means it's perpendicular to the radius. So I'm trying to get this here. I've got to rearrange it. So there it is. It's perpendicular to the radius, or it's tangential. 250 newtons. And at that radius, it's going to, it says applied to its edge, so it's at the full radius. Causes the wheel to have an angular acceleration of 0.94 radians per second. So we say alpha is 0.940 radians per second squared. So it's the angular acceleration. Okay. What is the moment of inertia of the wheel? And I had to give us a, well, no, actually we're going to back that out. So I was thinking we need a mass, but we're going to use Newton's second law to figure this out, because we need the dimensions and the mass to calculate the moment of inertia. We don't have that, so we're going to have to do it some other way. So Newton's second law says, for rotating system, it says that the sum of the torques is equal to the moment of inertia times the angular acceleration. So we're given angular acceleration, and if we can calculate the torque, then we should be able to back out what I is. So we're going to say that I is equal to the torque divided by the angular acceleration, solving for I. Well, the torque is just the force of 250 newtons acting through this distance, at this distance of 3.3 meters. So this is just going to be force times radius divided by alpha. So the moment of inertia is the force, which is 250 newtons, multiplied by the radius, which is 0.330 meters, divided by the angular acceleration, which is 0.940 radians per second squared. And we got everything in seconds, newtons, meters, so everything should be good shape. 250 times 0.33, which will give us a torque. Torque is 82.5 newton meters. And we divide by 0.94. And we get 87.7 kilograms meter squared, because that's the units for moment of inertia. What is the mass of the wheel? Well, if we know the moment of inertia is equal to a formula based on the mass and the radius, and because we have the radius, we should be able to also back out the mass associated with that. So the moment of inertia for a cylinder is 1/2 mass times its radius squared. So if we solve for the mass, we get 2I divided by R squared. So we have 2 times I, which is 87.7 kilogram meter squared, divided by R, which is 0.330 meters squared. 2 times 87.7 divided by 0.33 squared. That's 1,610 kilograms. So that's the mass. That's the moment of inertia. And third part says, if the wheel starts from rest, what is its angular velocity after 5 seconds have elapsed, assuming the force is acting during this time? So if this force continues to act, it will have a constant torque, which will give you a constant acceleration. So we just use kinematics here. What we're given is, we're given alpha, which is 0.940 radians per second squared. We have omega 0, which is 0. radians per second. And we have time, 5 seconds. And the question is, what is the angular velocity omega after 5 seconds? So which one of these involves, I'm trying to remember which one involves that, and we were trying to find the velocity. So, okay, so I'm thinking of the 4 equations. The one that comes to mind is omega 0 plus alpha t. That's the second equation. So we have omega 0, which is 0, plus alpha, which is 0.94 radians per second squared times the time, which I forgot to write it down here. It was 5 seconds. So we multiply by 5 seconds. Therefore, the rotational speed is going to be 0.94 times 5, 4.7. The units will be radians per second squared times seconds, which gives us radians per second. Okay, we're going to work problem number 36 on page 261, which is chapter 8. So if you can get your book out. And what we have is, of course, something rotating, because that's what we're talking about. So you have a potter's wheel, and it has a radius of 0.5 meters. And it says the moment of inertia, which we use the symbol I for that, moment of inertia of 12 kilograms meter squared. It says it's rotating at an angular acceleration or angular velocity of 50 revolutions per minute, which we're going to have to convert to radians per second. It says the potter can stop the wheel in 6 seconds. By pressing a wet rag against the rim and exerting a radially inward force of 70 newtons. So what will happen is, just like any kind of friction, you'll push in normally and then you'll get a friction force which is perpendicular to that application of the force, so it'll be acting tangent to the surface. So we know that it takes 6 seconds to finish. So this is going to be omega 0, and we know that omega is going to be 0 revolutions per minute, which is also going to be 0 radians per second. So let's convert. First thing we're going to do, convert revolutions per minute to radians per second. And if I remember correctly, it's lower in terms of radians per second, but we could also just look at it minutes per second. So we have 60 seconds per minute, and we have 2 pi radians per revolution. So you can see that's going to give us a number less than 50. So we take 50 times 2 times pi divided by, push the wrong button there, times pi divided by 60. So it's going to be around 5.23 radians per second. So what we're going to use is we're going to use the kinematic equations to solve for the angular acceleration, and then we can use Newton's second law to calculate the force that's needed to slow it down, and then we can take the ratio of the force tangentially to the force radially, and that can give us our coefficient of friction. So that's the basic problem solution. So given t and omega, the one we would use is that omega is equal to omega 0 plus alpha t. So alpha is equal to omega minus omega 0 divided by t. And omega is going to be 0. We subtract omega 0, which is going to be 5.23 radians per second divided by 6 seconds. So we get alpha. It's going to be negative because it's slowing down. So we get negative 0.87. And I'm just going to do two significant figures, radians per second squared. So that's our angular acceleration to slow this down. Okay, now we're going to use Newton's second law, which says the torque is equal to the moment of inertia times the angular acceleration. We also know that torque is going to be equal to a force acting through a distance. And the rag is going to be pushing in this way, and the friction force is going to be pushing perpendicular to the radius. So let me just draw my friction force in. So this is, we're going to have, let's say it's rotating, let me rotate it here. So we're going to rotate it this direction. So if it's rotating in that direction, then the force, the friction force, is going to be pushing backwards like this to slow it down. And if once it'll slow it down. Okay, so that's good. We'll call that F sub mu. It's the friction force. And we also have a normal force being applied here. It's actually in that direction. I'm trying to make it so I can copy it here. That's why I'm fiddling around. Okay, so that's our normal. That's going to be our normal force, and the ratio of those two forces is going to be our coefficient of friction. So this is F sub mu. So what we're going to be able to do is, if we substitute in for torque, we'll get the friction force times the radius is equal to the moment of inertia times the angular acceleration. So we can solve directly for it. The friction force, it'll be the moment of inertia times the angular acceleration divided by the radius. And the moment of inertia was 12 kilograms meters squared. The angular acceleration is negative 0.87 radians per second. And we divide by the radius, which is 0.5 meters. And so we have 12 times 0.87 negative divided by 0.5, we get 21 newtons. And that works out because we got radians, we got meters, we got everything's in meters, kilograms per second, so we know it's going to work out. So that's our friction force. It's a negative, and it's pushing in the opposite direction. So the opposite direction of motion. So that's why it's negative. So our coefficient of friction is just the ratio of the friction force to the normal force. So our friction force, we're going to use the magnitude, so it'll be 21 newtons. And from the problem statement, F sub n, the normal force, is 70 newtons. So we'll put that down there, 70. So 21 divided by 70 is 0.30. So that's our coefficient of friction, which is a ratio of two quantities, so there are no units. And let me just check the answer. So I've checked the answer book, and I've confirmed that is the correct solution. So again, just in review, because they give us this kinematic information of omega 0, the final omega, which is 0, and the time, we can calculate alpha from one of our equations. Knowing that alpha, we know that there has to be a force acting through a distance to create a torque that, in concert with the moment of inertia, we can use Newton's second law. And so we have the torque, which is the force times the distance, is equal to the moment of inertia times the angular acceleration. We're given this, we're given that, we calculated alpha. So we can solve for the friction force. We calculate that to be 21 newtons. The coefficient of friction is the ratio of the friction force to the normal force. So we just take 21 divided by 7, which is 0.3. Okay, this is problem number 40, which is a little bit more difficult than the one we worked in class the other day, but not significantly so. This covers a lot of elements in what we were doing. So we have a pulley. This pulley has some mass and some inertia to it, moment of inertia. Hanging off one side, we have a mass M1, which they show as being a circle. So it's a round mass. And then we have another mass hanging off the other side, which is M2, and they show it as a square mass. Okay, so it's called an Atwood's machine. We looked at this when we had a pulley that we considered to be massless and therefore no moment of inertia. And what's going to happen is if mass 2 is greater than mass 1, then it's going to move in this direction, which is what's the case here. So let's write it down. M1 is equal to 10 kilograms. M2 is equal to 20 kilograms. Okay, the pulley is a solid cylinder with mass M, so we have a big M of 8 kilograms. We'll put our little rotation thing, so it's going to rotate this direction based on the masses of the things hanging from there. The radius here R is equal to 0.200 meters. Okay, well let's go ahead and calculate the moment of inertia of the pulley. And it says it is a solid cylinder with a mass equal to 8 kilograms. So if we go to the table for these different elements, if I can find it here. Let's see, there's some graph, there's some listing of moment of inertia. There we go. Table 8.1, page 244. And for a solid cylinder or disk, it says the moment of inertia is equal to 1/2 the mass of the cylinder times R squared. So we have all the information necessary to calculate this. So we have 1/2. The mass is 8 kilograms. And the radius is 0.20 meters. And that's squared. And so our moment of inertia of the disk is 0.5 times 8 times 0.2, the quantity squared. So we end up with 0.16. The units are kilograms meters squared. So let's go ahead and put a box around that. So that's our moment of inertia. Now what we're going to do is we have to draw free body diagrams, and they're going to be three of them, one for this, one for that, and one for this. Now, interestingly enough, in the past, when we've had a pulley that has no mass, this tension is equal to that tension, but in this case, it's not going to be the case. This tension actually has to be greater than that tension so that you have a net torque. If they were the same, if you have the same force acting here as acting here, there would be no net torque, and therefore there would be no reason for this thing to rotate. So I'm going to create two screens here. We're going to draw free body diagrams of each element. So for the mass, M1, we have the weight. So the weight's going to be pulling down. It's not quite straight, but weight, which is going to be equal to M1 times the acceleration due to gravity. And let's define positive y's to go this way. We'll define positive y's and positive to be, except for this, which is we're always going to use counterclockwise as negative. So we're going to use positive y in this case. And then the other force acting on this is tension. We're going to call this T1. So that's T1. This thing has a mass of M1. And so let's go ahead and do the sum of the forces. Sum of the forces in the x direction. There are no forces in the x direction. So we have the sum of the forces in the y direction, and the sum of the forces in the y direction are going to be T1 is going to be positive, and the weight is going to be negative. I'm just going to go ahead and substitute in m1g for the weight, and it's going to move upward, so it's going to accelerate upward. So it's going to be positive acceleration. So we have m1 times a. Now I'm just going to use a because these are connected by strings, so this acceleration is going to be the same as that acceleration. Because if we move 2 meters up, we're going to move 2 meters down in that case. Okay, so that's the that's M1. So let's group all these, and I'm just going to squish them up a little bit so that we can keep all this on one page. And we can come back and look at that in a second. Okay, so the second one we're going to do, let's do it in blue, is the, actually we're going to do the disk now. So the disk has a radius, I'm not going to use blue. Okay, so the disk has a radius r, and it has two forces acting on it. Well, actually it has three forces, two that are important to us. We're going to have a tension here pulling down, and we're going to have another tension pulling down here. This tension is due to this object, and this tension is due to that object. We're going to call this T1 and T2. We're going to define positive as counterclockwise. There is another force. Let me use black. The third force is going to be the one that holds up the tensions, but we're only going to sum torques, and this force, which holds up the bearing, has no moment arm, and so therefore it doesn't have anything as far as contributing to the torque. So the two forces that contribute to the torque are the two tensions. Okay, so now we have the sum of the torques, and in this case we have two torques. We have this one, T1, has a distance r, so we're going to have T1 times r, and it's going to be positive because it's causing it to rotate counterclockwise, which we defined as positive. So we have T1 times r. And then we're going to subtract off this one because that's going to would have a tendency to go counterclockwise or clockwise. So we have T2 times r. So those are the sum of the torques. Force times distance, force times distance. Now, let's, since we're defining this as positive direction, we would also say this is positive acceleration here. So let's make that positive. So what we're expecting is we're expecting this to accelerate in the negative direction. So it's going to be negative. The moment of inertia, actually the negative goes with the angular acceleration, so alpha. So it's going to be negative. And if we guessed wrong, then we would get a negative answer. But if we guess this right, that it's going to cause the thing to go clockwise, then it'll work out. So that's the sum of the torques. This one doesn't contribute. This one is counterclockwise, which is positive, and this one is clockwise, which is negative. So that's our second equation. So let's group those together. Just move that up here. Make it a little smaller. Okay, so that's that. And then the third body is the second mass. So we're going to put our mass out here. And it's very similar to what we had for body 1. It's going to have a weight pushing downward. In this case, I'm going to define positive y downward. So this is going to be y. And that's so that when this is positive, this is also positive as far as acceleration, because this one will be going up and that will be coming down. So we're in good shape there. And then you have the tension pulling upward. So this is the tension. This is T2. Oops, got my thing crooked again. So this is T2. This is W2, which is equal to M2 times G. So we sum the forces in the y direction, and what do we end up with? Well, we have the sum of the forces in the y direction. We have, this is positive, so we have M2G. We subtract T2 off. And then that's going to be equal to the mass times the acceleration. So we end up with, let me write it down here, is equal to M2 times the acceleration, not times G. So, and we're expecting it to go downward, so we're just going to say that's equal to A. And this A is the same as that A. So we have now three equations. We have this one, and that one. We also have to find the relationship between alpha and A. And you can see if I have a positive direction for linear acceleration here, it's going to cause a negative direction in that, as far as the way we've defined it. So in our case, we can say that the acceleration, linear acceleration, is negative alpha times r. So we should have four equations and 4 unknowns, and we just have to do some substitution back in there. So let's move to the next page and put it all together. So let's write all these equations down. We have T1 minus M1G is equal to M1A. So that's from the sum of the forces. The sum of the torques say T1R minus T2R is equal to negative I alpha. That's from the sum of the torques. Third equation is M2G minus T2 is equal to M2A, and we have that the linear acceleration is negative alpha times r. So what are our unknowns? We don't know T1, we don't know T2, we don't know A, and we don't know alpha. Everything else we know. So we have 4 equations and 4 unknowns. That means that we can solve this. And we're going to try to do it by substitution. So I think, so we'll think about this. The first one is to substitute in here so we can get it either in terms of alpha or A. So let's put it in terms of A, just because there's only one equation with A. So we can rewrite the second equation as T1R minus T2R is equal to, and since we have a negative times a negative, we'll have I times R. Is that right? No. So if we substitute, if you solve for alpha, alpha is negative A over R. So the negative signs cancel out, but we still have A over R. And probably the best thing to do is to solve, what is the best thing to do here? Probably the best thing to do is solve this one for T1 and plug it in here. Solve this one for T2 and plug it in there. And the only unknown we have then is acceleration. So let's do that. So let's take the first equation. T1 is equal to M1A plus M1G. If we take this equation and solve for T2, that's going to be equal to M2G minus M2A. Okay, now we're going to plug in here. Let me put up another page. So for T1, we'll put in M1A plus M1G, and that's going to be multiplied by the radius. Make sure we have enough space to do all this. Here we'll have negative. T2 is M2G minus M2A, also multiplied by R. And that's going to equal IA over R. So if we take the two terms involving acceleration, let's see what we can get. We get a times r, because these both are multiplied by r, times m1a, and we've got negative, so we'll have plus m2a. So that's this times that, and that times that. Okay. Actually, we don't need the a's in there. We just need the masses. So let me get rid of that. So we just need m1 plus m2. So we get m1 plus m2. Oops, I was trying to group those. Okay, so we group those two. And then we have this part. So we can factor out g. So we'll have g times r. And that'll be m1 minus m2 from this one here. And that's going to be equal to I a over r. And then we'll subtract this from both sides, and we'll add that. We'll subtract this from both sides, and we'll subtract that from both sides. So what you end up with is you'll have AR times m1 plus m2 minus I a over r is equal to, what I'm going to do is I'm going to just change the sign. So we'll have m2 minus m1, so m1 minus m2. Now if I factor out an a, and yeah, what am I going to do here? We can move the r in and then just factor out an a. So we'll have a times r m1 plus r m2 minus I over r. Okay, so we're factoring out an a. And that's equal to g r m2 minus m1. And now we can solve for the acceleration. It's going to be gr m2 minus m1 divided by r m1 plus r m2 minus I over r. Okay, before we finish, I have one correction to make, and that is this. I think I double dipped here by assuming that alpha was going negative, and then I made this assumption here, and because of that, I either have to take the negative sign off of here, or I have to take the negative sign off of there. So what I'm going to do is I'm going to make that positive, and what that will do is, actually, no, it won't. Actually, I do need to keep that negative. I knew there was a negative sign issue problem here, and I forgot the negative right there. So the negative, that becomes positive, that's positive, and that's positive. I knew it had to be a positive there, and I knew I did something wrong. So anyway, I forgot the negative sign, so it was okay. Didn't overdo it. So now to find the solution, all you have to do is just plug in the numbers. So the acceleration is equal to g, which is 9.8 meters per second squared. The radius for the problem was 0.2 meters. M2 was 20 kilograms. M1 was 10 kilograms. And then we divide by 0.2 times 20 plus 0.2 times 10. Actually, it's the other way around. M1 is 10, M2 is 20. Okay, so let's fix that. So some confusion later on. Okay, so M1 was 10, M2 was 20. The moment of inertia was calculated to be somewhere back here, 0.16. 0.16 kilograms per meter squared divided by 0.2. Now I could have factored out an R. You know, I could cancel these out and you'd end up with the R's going out and you have I over R squared. So if you plug the numbers in, 9.8 times 0.2 times 10, which is 20 minus 10, divided by 0.2 times 10 plus 0.2 times 20 plus 0.16 divided by 0.2. I get 2.88. So the acceleration is as expected, going up. The acceleration should be less than 9.8 meters per second squared, because what's happening, basically what's going on here is this is the thing that drives the movement. If the weights were the same, the masses were the same, there would be no reason for it to rotate. But because they're different, and the more different they are, the more quickly they rotate. These are the inertias associated with the system. So you've got the inertia of mass 1, the inertia of mass 2, and the inertia associated with the rotating element. So the larger the inertia is, the slower the acceleration. The larger the difference in the weights and the masses, the larger the acceleration. So the more mass you have in the system, the more difficult it is to accelerate, and the lesser it will be compared to standard free fall. So that's the acceleration. Now to find any of the other things, you just have to plug it back in to the equation. So if we were to, let's just copy these over. So these were the sum of the forces in the different directions. So if we want to find T1, that's just going to be equal to M1, which is 10 kilograms, times the acceleration, which is 2.88 meters per second squared, plus M1, which is 10 kilograms, times 9.8 meters per second squared. And so we get 10 times 2.88 plus 10 times 9.8. So T1 is equal to 127 newtons, and T2 is equal to M2, which is 20 kilograms, times 9.8 meters per second squared, minus M2, which is 20, times the acceleration, which is 2.88. And so what we get is T2 is equal to 20 times 9.8 minus 20 times 2.88. And we get 138.4 newtons. So T2, the tension under T2 is greater than T1, and that's because this difference in these forces are causing the object to rotate, causing the disk to rotate. This has to be greater than that before you have a net torque that's going to cause it to rotate clockwise. So that makes sense. And I have checked the answer, and that is the correct solution. So we're all good to go. This is problem 42, chapter 8. So it's on page 262. If you want to pause it to get the book so you can read along. So let's read it. A car is designed to get its energy from a rotating flywheel with a radius of 2 meters and a mass of 500 kilograms. So let's draw our flywheel. And it has a radius. The radius is 2 meters. And the mass of the flywheel is 500 kilograms. next sentence. Before a trip, the flywheel is attached to an electric motor, which brings the flywheel's rotational speed up to 5,000 revolutions per minute. So we're going to say that omega is equal to 5,000 RPM. Probably going to want to convert that to radians per second at some point. Find the kinetic energy stored in the flywheel. So let's just write down what is the kinetic energy for a rotating body. It's 1/2 moment of inertia times omega squared. So we know omega, the initial omega. We're going to have to convert omega to radians per second, which, remember, it's 2 pi divided by 60, and hopefully getting to the point where we remember that radians per second are less than revolutions per minute. So we know to multiply by 2 pi, which is around 6, and divide by 60. So it's going to reduce it close to a factor of 10. So we have 524 radians per second. So that's the rotational speed. The moment of inertia, we need to use the mass and the radius. And for a cylinder, is what we're deciding it is. The moment of inertia for a cylinder is 1/2 the mass times the radius squared. So we can go ahead and calculate the moment of inertia. So the mass is 500 kilograms, and the radius is 2 meters, and we square that. So we have 0.5 times 500 times 2 squared. So we get 1,000. And the units are kilograms meters squared. So to find the kinetic energy, all we have to do is plug into the expression for kinetic energy. And kinetic energy should be in joules. So we have 1,000 kilograms meters squared times omega, which is 524 radians per second, quantity squared. So the kinetic energy, 0.5 times 1,000 times 524 squared. And we get this big long number, and if you count the number of decimals before the 1, it's 1 point something. You count 1, 2, 3, 4, 5, 6, 7, 8. So it's 1.37 times 10 to the 8th joules. You get kilogram meters squared per second squared, and that's the unit for a joule. It's a newton. Newton is a kilogram meter per second squared times meters. Newton meters is a joule, so the units are good. Okay, so that's part A. Part B. If the flywheel is to supply energy to the car as a 10 horsepower motor would, find the length of time the car could run before the flywheel would have to be brought back up to speed. So this is the total energy, and all we have to do is figure out what's 10 horsepower in joules. So there's a conversion factor. Horsepower is also energy. So you go to the front of your book and you look under work energy, and you see that where are we? Actually under power. Because horsepower is actually joules per second. It's work per unit time. So it says the conversion says 1 horsepower equals 0.746 watts. And a watt is a joule per second. So this is joules per second. So 1 horsepower equals that. So if we multiply by 10 horsepower equal 7.46 joules per second. So this is a rate of change of energy. You can see we have units of joules here. So to find seconds, we're going to divide this joules by joules per second, and we'll get seconds. So the time is going to be equal to, basically we're going to take the energy, kinetic energy, and divide by the power. The energy is in joules. The power is in joules per second. And that's the same as taking joules times 1 over that, which is seconds per joule. So the joules cancel out and you get seconds. So that's all good. So the time is equal to 1.37 times 10 to the 8th joules divided by 7.46 joules per second. And I'm just checking the, oh, actually I knew there was something wrong. It seemed too big. It's actually kilowatts here. So this is kilojoules, and so this is kilojoules. So what we're going to do is if you multiply it by 1,000, you'll get joules. There are 1,000 joules per kilojoule. So now we'll get time in seconds. So 1.3, okay, so divide by 7.46 and divide by 1,000. And I get 18,400 seconds. And if we want to convert that to hours, you divide by 3,600, and we'd end up with 5.1 hours. So I'm going to pause it and make sure. So I've checked the solution, and I have worked it correctly. So we're in good shape. Okay, this is going to be an interesting one. This is problem number 46. And so let's just look at it. It's on page 262. It's a fairly short problem, but it does require some insight into what's going on here. But we have a 240 Newton sphere, so it's going to be like a ball. And so there's the ball, and so let's write these facts down about it. So the mass, sorry, let's write the mass. Actually, it is the weight. The weight is 240 newtons. The radius of the sphere is 0.2 meters. And it rolls without slipping 6 meters down a ramp. So let's draw a ramp. So we'll start here at the top of the ramp, and we'll go down to the bottom of the ramp. Of course, it looks like the ball is huge, but it's not really drawn to scale. Okay, so rolls 6 meters without slipping 6 meters down a ramp. So the distance 6 meters is going to be this distance right here. It's going to be the distance from the top to the bottom. So that's 6 meters. And the ramp inclined at 37 degrees. So this is 37 degrees. What is the angular speed of the sphere at the bottom of the slope if it starts from rest? Okay, so this is a kinetic energy problem. And what's going to happen is we're going to exchange potential energy. We're going to decrease the potential energy by not 6 meters, but whatever this height is. And that's going to result in two kinds of kinetic energy. There's going to be translational kinetic energy and rotational kinetic energy at the bottom. So let's just write this down. So what we have is we have the change in kinetic energy plus the change in potential energy equals 0. There are no external forces acting on this. Now it rolls, but so there's a force acting to keep it from sliding, but that force doesn't act through a distance. So it just comes down to the sum of the kinetic energies plus the sum of the potential energies equals 0. So the change is the initial minus the final. So let's do the first one. Let's do linear kinetic energy. So we have V final squared minus V initial squared. So that's the change in kinetic energy, linear kinetic energy. The change in rotational kinetic energy is going to be equal to I times omega final squared minus omega initial squared. So those are the two kinds of kinetic energies we're going to end up with. Our initial kinetic energy is 0 because it starts out at rest. And then we add on the potential energy change, which is going to be G times M times the final height minus the initial height. And that's all going to equal 0. So let's mark what we can mark as being 0 here. So the initial velocity is 0. The initial rotation is 0. And the difference in height, it's going to be, the final height is going to be lower than the initial height. So, and it's going to be this distance here. So this is going to be h final minus h initial. But it's going to be, we're going to have a decrease in potential energy. So using the fact this is the opposite side, this is the angle, this is going to be equal to 6 meters times the sine of 37 degrees. So let's go ahead and calculate that. 6 times the sine of 37 degrees. So we get 3.61 meters. That's the vertical height difference. Okay, we're given the weight, and we need the mass, so let's go ahead and do that. So the mass is equal to the weight divided by g, just like the weight is the mass times gravity. So the weight was 240 newtons divided by the acceleration due to gravity, which is 9.8 meters per second squared. So 240 divided by 9.8 is 24.5 kilograms. Now, what else do we need? We need, well, we know what the acceleration due to gravity is, we know the mass, we know what that is. The moment of inertia. The moment of inertia of a sphere, we have to go back in the book and look this up. It's not equal to the same. It's not the same as a cylinder. Moment of inertia of a solid sphere is 2/5 mr squared. So we get 2/5 times the mass, which we just calculated to be 24.5 kilograms, times the radius, which was 0.2 meters, that's squared. So 2 divided by 5 times 24.5 times 0.2 squared. And so we get the moment of inertia to be 0.392 kilograms meters squared. Now the only thing we have left is we need to write v in terms of omega. And what we know is that the velocity is equal to omega times r. So this applies. Now we're going to be rotating around this center, so the omega is, it's a little bit, seems like a little more confusing, but the linear velocity is here and we're rotating around this center, so we still have r. The actual r distance is from here to there, but it's still related. So we can write this either in terms of omega or in terms of r, depends on what we want to solve for. And so let's go back to the problem statement and see if there was a particular, what they were asking for. What is the angular speed? So they're asking for omega, so it makes sense to rewrite this equation in terms of omega. So let's do that. So we get 1/2 times m. Okay, so v final is going to be equal to omega r squared. So that's v sub f squared plus 1/2 I times omega. So this is omega final squared, plus this change in kinetic energy. I'm going to go ahead and put it in here, and it's going to be negative. And oh, actually, let's wait a second here. Yeah, let's go ahead here. So let's put mg times negative 3.61 meters. And I'm going to do one more step just so I can cancel something out here. So you got 1/2 m, you've got omega final squared r squared plus 1/2 times the moment of inertia. Yeah, it might be just better just to stick things in here. So let me just leave this. I was going to put moment of inertia in terms of mass, but I've already calculated it, so it probably is just as easy to continue on from here. And that whole thing is equal to 0. So if you factor out omega final out of the first two terms, omega final squared, you get 1/2 m r squared from this term. You get 1/2 I from the second term. And then we have plus mg times negative 3.61 meters is equal to 0. So you can see that we can solve for omega final squared. So let's do that. Omega final squared is equal to, what we're going to do is we're going to subtract mg times minus 6.1 meters from both sides. So that'll become positive. So we'll have mg times 3.61 meters divided by this term in the parentheses, which is 1/2 m r squared plus 1/2 I. So let's plug the numbers in, and then we'll get an omega squared, and then we'll take the square root. So the mass was equal to 24.5 kilograms. The acceleration due to gravity is 9.8 meters per second squared. The change in height was 3.61 meters. We divide that by 1/2 times the mass, which is 24.5 kilograms, times the radius, which was 0.20 meters, and we square that, plus 1/2 times the moment of inertia, which is 0.392 kilograms meters squared. We get that from right over here. So let's plug in our calculator. So follow along. 24.5 times 9.8 times 3.61 divided by the quantity 0.5 times 24.5 times 0.2 squared plus 0.5 times 0.392, close the parentheses, and we get 1264. And this would be radians squared per second squared. And if you take the square root of that, you will get the final angular speed to the 0.5 power, and we get 35.5 radians per second. So I'm going to pause it, check the answer, and then we'll come back and kind of review what happened here. So Eureka, I got it right. So let's kind of go back here, review what we did. What we did was we said we had a ball that was a ball sphere that was on the top of this ramp that had no kinetic energy, either rotational kinetic energy or translational kinetic energy. When this thing rolls down, it's going to roll down the hill, and it's going to exchange potential energy for kinetic energy. And it says we know that the sum of the kinetic energy, the change in kinetic energy plus the change of potential energy equals 0. What we lose here, we gain there, and we just switch it back and forth. So if we look at the kinetic energy, there are two kinds of kinetic energy: translational kinetic energy and rotational kinetic energy. And then we have our potential energy. So the translational kinetic energy is 1/2 mv squared. So the change would be v final squared minus v initial squared. The rotational kinetic energy is 1/2 I omega squared. So we take omega final squared minus omega initial squared. And our potential energy is the mass times g times the change in height. the final height minus the initial height. The final height is going to be lower than the initial height, and we calculated that by using right triangle geometry, knowing that the hypotenuse was 6 meters. This angle is 37 degrees, so the opposite side length is going to be 3.61 meters, sine of 37 times 6 meters. So that's the change in height, and it's actually a negative right there because it gets less. So we're going to use negative 3.61 here. So we look at what we know and what we don't know. Well, we can set the initial velocities and the initial rotational speed to 0 because it's stationary. We need to calculate the mass. So we were given the weight. So knowing the weight, we can divide by the acceleration due to gravity and get the mass. So we know that. We're trying to solve for both the rotational speed and the linear speed. The moment of inertia is for a sphere. You go to the book, you find the equation over here on the second page is 2/5 mr squared, so we get 2/5 times the mass times the radius squared, and that gives us 0.392 kilograms per meter squared. So we know I, we know G, we know M, and we know this is negative 3.61. So this is the equation on the second page which applies, and that all equals 0. So let me just move this over a little bit and make it 0. Now, what else do we do here? We multiplied this out, so you got omega final squared times r squared. Oh, I know what we did. We related the translational speed to the rotational speed through the equation that we know, v is equal to omega r. So for v final, we put in omega final r, and we square it. So now this equation, the only unknown is the final rotational speed. So we factor out omega final squared out of the first two terms. That leaves 1/2 mr squared and 1/2 I. Then we have our potential energy change. So if we subtract this from both sides, which we'll get it to the right-hand side, and then divide by this term, we can solve for omega final squared, which is what we do. So that's the expression. And then we plug the numbers in. Mass G, the change in height. And again, the negative was over here, so when I added it to both sides, then it became positive. If it was negative, we'd be in trouble because we'd be taking the square root of a negative number, and that would be imaginary. Okay, the denominator is 1/2 mr squared plus 1/2 I. So we plug those in. We get omega final squared is 1264 radians squared per second squared. If you did the units here, you'd get 1/second squared, but since we're dealing with rotational speed, we put the radians in there, which are unitless, but they are still important. And you take the square root and you get 35.5 radians per second. Okay, we are on problem number 52. And we actually solved a problem like this in class using Newton's second law, and we're going to solve the same problem using energy methods. So what it is, it's a bucket on a spool, and so this thing pulls down with a force which causes the thing to rotate. So let me put my bucket in here. Okay, so that's the drawing. Let's see what it says. It says the diameter. So let's write it. Show a diameter here. The diameter is 0.6 meters. The mass of the pulley is 5.00 kilograms. And the mass of the bucket is 3 kilograms. And it says, determine the angular speed of the spool shown in figure 8.52 after the 3 kilogram bucket has fallen 4 meters. So we know that delta Y is 4.0 meters. Starting from rest, the light string attached to the bucket is wrapped around the spool and does not slip as it unwinds. So we could have, you could do free body diagrams of this element and this element, and you could figure out what the tension the string is and the acceleration, etc., etc. But using energy methods, because there are no external forces applied, we know that the change in kinetic energy plus the change in potential energy is equal to 0. And so we have the change in potential energy associated with the bucket dropping. There's no change in potential energy of the pulley. It's at the same height the whole time. But it does increase in kinetic energy. So we have, again, two kinds of kinetic energy. We have translational kinetic energy, which is going to be 1/2 the mass of the bucket times the velocity of the bucket squared. And let's actually put this in final and initial versions values, and then we can set some of them to 0. So what we'd have is 1/2 the mass of the bucket times the final velocity of the bucket squared minus the initial velocity of the bucket squared. So that's the change in kinetic energy associated with the translation. And then we have rotation, which would be 1/2 the moment of inertia times the final rotational speed of the pulley minus the initial rotational speed of the pulley squared, both of them squared. So that's the change in kinetic energy associated with this thing, or rotating, plus we have the mass of the bucket times the acceleration due to gravity, and the final height minus the initial height. And all that stuff equals 0. So let's call this the mass of the bucket. This is the mass of the pulley. This is the radius. So we can calculate, we know the mass of the bucket. We know that this is 0 because it starts from rest. We know that's 0, so that starts from rest. We know that H final minus H initial is going to be negative 4.0 meters. So we need to calculate the moment of inertia, and we also need to relate the final velocity of the bucket to the final rotational speed of the bucket. So the moment of inertia is pretty easy. We're assuming it's a disk, so it's going to be I is equal to 1/2 mr squared. That's the mass of the pulley. So we get 1/2 the mass of the pulley, which is 5 kilograms, times the radius of the pulley, which is 0.60 meters. We square that. So the moment of inertia of that is 0.5 times 5 times 0.6 squared. So we get 0.9 kilograms meter squared. And again, we can relate rotational speed to linear speed by this. We know that the linear speed of this point on the wheel is the same as the linear speed of the bucket dropping. So we know that V, in this case of the bucket, is equal to omega of the pulley times R of the pulley. So we can make those substitutions in. So let's do that. 1/2 mass of the bucket, and we're trying to find the rotational speed of the spool, so we're going to solve for this, and we'll just use omega. So we're going to have omega times R squared plus 1/2 I times omega squared. And I've taken the F off of there because we know that's what it is, plus mg H final minus H initial, and that equals 0. So if we subtract this from both sides and factor out omega, we'll get omega squared is equal to 1/2 mass of the bucket times the radius squared plus 1/2 I is equal to the mass times G times H initial minus H final. I changed the sign because I went to the right-hand side. And then if you solve for omega squared, you'll find it as mass times gravity times H initial minus H final divided by all this stuff here, 1/2 mass of the bucket times the radius squared plus 1/2 I. So now we can plug in and get a number, and then we'll take the square root. So omega squared is the mass, and that's the mass of the bucket, which was 3 kilograms, times the acceleration due to gravity, which is 9.8 meters per second squared, times the height. In this case, it's positive 6 meters. Make sure I'm getting that right. 4 meters. I don't know where I got 6 meters from. 4 meters. Let's go back and see if I have to correct that. No, it's 4 meters. I don't know where I was thinking 6. Probably from a previous problem. Okay, that's all divided by 1/2 the mass of the bucket times the radius, which is 0.60 meters squared, plus 1/2 times the moment of inertia, which is going to be equal to 0.900 kilograms meters squared. And you can see the kilograms cancel out with this kilograms. You got meter squared per second squared divided by meter squared leaves you inverse second squared, which is the same as radians squared per second squared. Okay, plug in the numbers. 3 times 9.8 times 4 divided by the quantity. 0.5 times 3 times 0.6 squared plus 0.5 times 0.9, close parentheses, and we get omega squared is 118, and it'll be radians squared per second squared. So you take the square root, and we get 10.9. 10.9 radians per second. And I've checked the answer book, and I am correct again, so that's great. This is problem 55, page 263, chapter 7. And this one is basically looking at the comparison of the angular momentum associated with the Earth as it does two things. One as it spins on its axis, and one as it rotates around the sun. So as it spins on its axis, what we have to do is we have to calculate the angular speed that the Earth rotates and its moment of inertia, because the angular momentum of any body is just the product of the moment of inertia and the angular speed. So as long as we have these two things calculated, it's just a matter of plugging in the numbers. So part A, we just have to calculate each one of these. So it takes 1 day to rotate the Earth. And if we go back to our cheat sheet for chapter 7, we have an expression that relates the period to the rotational speed. So the rotational speed of a rotating object is equal to 2 pi divided by the period. And in this case, our period is we need to convert from days to seconds. So we'll have 2 pi divided by 1 day, and then we're going to multiply by 24, which is 24 hours per day, times 60 minutes per hour, times 60 seconds per minute. And so that will give us the period in days, and the period in seconds, and then we just have to plug into the equation. So let's see what we get. So we get 2 times pi divided by the quantity, 1 times 24 times 60 times 60. And so we end up with this period, the rotational speed of 7.27 times 10 to the minus 5th radians per second. So it's pretty small. So that's our rotational speed. And our moment of inertia, we assume, according to the problem, we treat it as a sphere. So we go into the book and look for the equation for the moment of inertia of the sphere rotating about its axes in the center. And I'll find it here in just a second. And so for a solid sphere, so we're assuming that it's uniform throughout, which is not exactly correct, but it's going to be close enough for government work. So we have 2/5 times mr squared. So we need the mass of the Earth and the radius of the Earth. So I'll have to go back to chapter 7 for that. And those are given on table 7.3 on page 217. So let's write those down. Let's go ahead and write down all the information we'll need even for the second part of the problem. So the mass of the Earth is equal to 5.98 times 10 to the 24th kilograms. The mean radius of the Earth is equal to 6.38 times 10 to the 6 meters. And the only other thing we need is the radius. Let's use a small r here. This is the radius of the Earth. And we need the radius, which is the distance from the Sun to the Earth. And that is 1.496 times 10 to the 11th meters. And actually, it's in the table. So the period for one orbit of the Earth in seconds, so we don't have to calculate this. 3.156 times 10 to the 7th seconds. So if we took this number here and divided and multiplied by 365, we get something like that. Of course, it's not exactly 365. It's 365 and a quarter approximately, which is what we're having this year. We're having a leap year. Okay, so the moment of inertia of the Earth as it rotates about its own axis is 2/5 times the mass of the Earth and we multiply by the radius of the Earth, and we square that. So let's do the calculation. 5 divided by 2 times 5.98 e to the 24th times 6.38 e to the 6th power, and we want to square that entire thing. So I'm going to insert some parentheses in there, so make sure that it squares the entire quantity. So I get 9.74 times 10 to the 37th power, and the units of moment of inertia are kilograms per meter squared. So now we have both the rotational speed and the moment of inertia, so we can calculate the angular momentum. So our moment of inertia is that, and our rotational speed is this. So we multiply those together. And I get 7.1 times 10 to the 33rd. And the units are kilograms meters squared per second. So that's the moment of the angular momentum of the Earth revolving around its axis. For part B, we treat the Earth as a point mass, meaning that we're saying that the dimensions of the Earth are small in comparison to the radiuses that we're dealing with. And you can see that's the case because the diameter of the Earth is 10 to the 6th. The distance from the Sun to the Earth is 10 to the 11th, so it's on order of 100,000 difference times 100,000 times difference. So definitely in this case it's a point mass. So for part B, the moment of inertia is just going to be mr squared. This is the mass of the Earth, and this is the distance from the Sun. So we take the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, and we'll multiply by the distance from the Earth to the Sun, and we square that. So let's put that in the calculator. Put 496 e to the 11th. We square that. 5.8 10 24th. Okay. So we get the moment of inertia 1.34 times 10 to the 47th kilogram meter squared. So that's the moment of inertia. You can see it's significantly larger than the moment of inertia of the Earth revolving on its axis. And we already have the period, so the relationship between the period and the rotational speed is the same one we had before. So the rotational speed is going to be this divided by 365, basically, close to it. So we have 2 pi divided by the period, which we have written down on the previous page, 3.156 times 10 to the 7th seconds. So we take 2 times pi divided by 3.156 e to the 7th. And so rounds off to about 2.0 times 10 to the minus 7th radians per second. So all now we have to do is multiply these two terms together, and we get the angular momentum associated with the Earth revolving around the Sun. So our second angular momentum is again the product of the moment of inertia and the rotational speed. So we'll plug that in. And so multiplying those together, we get 2.7 times 10 to the 40th, and it's going to be kilograms meter squared per second, same units as previously. So if we compare these two between A and B, we've got an order of magnitude of 10 to the 7th, which is huge. So most of the angular momentum associated with the Earth is associated with it revolving around the Sun. Only a very small amount is associated with it revolving around its axes. And I checked the answer, and that is the correct answer. The only additional comment is that we can change the units in terms of angular momentum. If we look at, let's just look at the units of work. So the units of work, which are joules, is force acting through a distance. And force is newtons, and newtons are kilograms meter per second squared, because it's mass times acceleration. So that's force times distance, which is meters. So we get kilogram meter squared per second squared. So that's a joule. And if we multiply by seconds, so we multiply this by seconds, we'd have joule seconds, which would be the same as our units up here, kilogram meter squared per second. So we can say this is also 2.7 times 10 to the 40th joule seconds, and we could say the same thing down there. This is problem 70 on page 265. So you're probably looking at this and saying, oh God, it's one of those inclined plane kind of problems. So anyway, we'll deal with it here. So if you have your book open, we have a 12 kilogram object is attached to a cord that is wrapped around a wheel of radius 10 centimeters. The acceleration of the object down the frictionless incline is measured to be 2 meters per second squared. Assuming the axle of the wheel to be frictionless, determine A, the tension in the rope, the moment of inertia of the wheel, and the angular speed of the wheel 2 seconds after it begins rotating, starting from rest. So the first thing we're going to do is we're going to draw a diagram of this thing. So I've got the inclined plane, I've got the block, which will rotate, and then we have the pulley up here. Okay, then we have a rope that's attaching the pulley to the mass here. Okay, probably need to make the box just a little bit bigger so that this thing, I can move this up and put that tangent to the pulley. Okay, so what we're looking at is we can do a free body diagram on the block, and we can do a free body diagram on the pulley. So the first thing we're going to do is just on the block. So let me just copy this. Oh, I thought I was going to copy it. I've got to paste it. Once I copy it, paste it. There we go. Okay, so what forces do we have acting on this body? Well, we have the tension in the rope, and we have the weight, which is going to be pushing downward. And because it's frictionless, there's no force between here and here in the direction of the ramp. And because it's on a ramp, we're going to align our axes so that you have, this is going to be Y, and this is going to be X. So that's X and Y. And in reality, the Y stuff has nothing to do with anything. Well, we also have, I forgot one thing, we have the normal force here that's holding it up so it doesn't go into the ramp. So there's got to be a normal force. So this is the weight, and this is the normal force. There's no friction force because that's stated in the problem. Okay, so if we do the sum of the forces in the X and Y directions, the sum of the forces in the Y direction are equal to 0 because there's no movement in the Y direction. And we have F sub m, which is pointing upward. And what we have pointing the other direction is the Y component of the weight. So remember, we'd have this component, the X component of the weight, and the Y component of the weight. And this is the angle theta right here. Same as the angle of theta here, which is the angle of the ramp. So the Y component, this component right here, because it's the adjacent side to, so this is W, make sure I get the W in the right place. So weight is pointing downward towards the center of the Earth. So this side, which is the adjacent side, is going to be equal to W times the cosine of theta, which is the trig function that involves the adjacent side. And this one is going to be W times the sine of theta. And you kind of think, if this thing had a 0 angle, the angle went to 0, then all the force would be towards the ramp. and the cosine of 0 is 1. So that makes sense. So we have the normal force pushing in the positive y direction. We have the weight pushing in the negative y direction. So this is going to be negative W times the cosine of theta. And that really doesn't give us any information that we need, but that is the sum of the forces in the y direction. Now the sum of the forces in the x direction, we just have, in this case, because it is moving along here, we have the mass of the block times the acceleration, and that is equal to, in the positive x direction we have this tension, and in the negative x direction we have W times the sine of theta. So that's the sum of the forces in the x direction. Now the acceleration, it says it's down the ramp. So it's going to go this direction. So our acceleration is actually negative. So let's put a second screen up. So let's see what we know from the problem statement. We know that theta is equal to 37 degrees. We know that the mass of the object is 12 kilograms. We know, what else do we know? We don't worry about the radius right now. The acceleration is going to be negative 2.00 meters per second squared. It's negative because it's going to go that direction, and our positive x direction is going up the ramp. So let's look at the sum of the forces and see what we know. We know the mass, we know the acceleration, we can calculate the weight. The weight is always just the mass times the acceleration due to gravity, so let's plug that in. Mass is 12 kilograms times 9.8 meters per second squared. So we have 12 times 9.8. So the weight is 117.6 newtons. Okay, so back to the equation. We know that, and we know the sine of theta. So the only thing we don't know is tension, which is the question for part 1. So we don't even have to worry about the pulley in this case. We just solve this equation for tension. So it's going to be equal to the mass times the acceleration plus the weight times the sine of the angle theta. So we have 12 kilograms. Our acceleration is negative 2.00 meters per second squared, and we add the weight, which is 117.6 newtons, and we multiply that by the sine of the angle, the sine of 37 degrees. So plug that in the calculator. We have 12 times negative 2 plus 117.6 times the sine of 37 degrees. Make sure my calculator's in degrees, which it is. And so I find out that the tension is 46.8 newtons. Okay. Now, I didn't do the free body diagram at this part yet because I asked the question, can I solve the problem without going to this part? At least solving part A. And the answer was yes when I looked at what I knew and what I didn't know. Okay, so that's part A. Part B says, what is the moment of inertia of the wheel? Well, if we do a free body diagram on the wheel, let's do that. So we can't just pick that out of thin air. So we know the tension on the wheel. So let's draw what's happening here. We have a tension, which is going to rotate this thing counterclockwise. So it's going to go this way. This is our tension. And then there's a radius associated with this wheel. So that's R. And when you sum the forces around, or sum the torques on this wheel, what we find out is the sum of the torques is going to be equal to, instead of mass times acceleration, we use the moment of inertia times angular acceleration. And that's equal to the sum of the torques, so that's all we have. And the only torque that we have acting on this is the one associated with this tension. We have another force here, which would be holding this thing up. Actually, you'd have a force probably acting in somewhat that direction because you have the mass of the pulley and you have this tension. So, but the thing is that those forces are all acting right here at the center of rotation. And so those don't contribute as a torque to this equation. The only force that's acting at any distance from the radius is this tension. And it's going to cause a counterclockwise rotation, therefore it's going to be a positive torque. So we know that. So the sum of the torques is only 1, and it's going to be equal to the tension times the radius. So we know the tension, we know the radius, so we know this part. We may not think we know the angular acceleration, but we can relate angular acceleration to linear acceleration through this relationship. The linear acceleration is the angular acceleration times the radius. And we know this, and we know that, so we can calculate alpha. So we know that, we know that. The only thing we don't know is the moment of inertia, which means that's the answer. That's how we're going to solve the second part of the problem. So now one thing we have to be careful about is the sign here. If you have positive angular acceleration here, you're going to have negative linear acceleration here. So we really are going to put a minus sign here to reflect that reality. So if we take this, we'll have the moment of inertia is equal to the sum of the torques divided by the angular acceleration. So for the sum of the torques, we put in the tension times the radius. And for alpha, we put in negative, if we solve for alpha here, we get alpha is equal to negative A over R. So we put negative A over R. Now when you divide by a fraction, it's the same as multiplying by the reciprocal. So what we'll end up doing is getting T R squared over A. So I'm take the reciprocal of this, which is R over A. So the A stays in the denominator, and the R times the R becomes R squared. So now all we have to do is plug the numbers in. So the moment of inertia of the wheel is negative the tension, which is 46.8 newtons, times the radius, which is 10 centimeters, which is 0.01 meters. And we square that, and we divide by the linear acceleration, which is negative 2.00 meters per second squared. And you see the negatives cancel out, so we end up with a positive moment of inertia, which has to happen. 46.8 times 0.1 squared divided by 2. So we find out that the moment of inertia is 0.234, and the units for moment of inertia are kilograms meters squared. So that's part B. And then finally, the angular speed of the wheel 2 seconds after it begins to rotate, starting from rest. So the third part of the problem is just a kinematics problem, because we know that alpha is equal to, well, we can calculate it. It's equal to negative A over R, so let's do that. Negative A, which is negative 2.00 meters per second squared, divided by the radius, which is 0.1 meters, or 10 centimeters. So we'll end up with 2 divided by 0.1. So it's 20. That's 20 radians per second squared. So that's alpha. So we know alpha. We know that the time is 2 seconds. That's given in the problem. And we know that omega 0 equals 0 radians per second. So we know 3 out of the 5. The things we don't know are the final angular speed and the total angle that the thing rotates through. So they're only asking us for omega. And of the equations that we have omega is equal to omega 0, plus plus alpha t. That's our second equation, and that's the one that we'd want to use because we have omega 0, we have alpha, and we have t. So to find omega, we just plug in omega 0 is 0 plus alpha, which is 20 radians per second squared, times time, which is 2 seconds. And so we find out that omega is 2 times 20, which is 40 radians per second. And it's positive because if we have positive acceleration, which is counterclockwise, we're also going to have positive rotational speed. So omega is equal to 40. And that's the answer. Okay, we have problem number 72, chapter 8. So hopefully you have your book ready. We have two astronauts, each having a mass of 75 kilograms, and they're connected by a 10-meter rope of negligible mass. They're isolated in space, moving in circles around the point halfway between them at a speed of 5 meters per second. So let's just draw what's happening here. So we're going to represent the people just by circles. So we got one person here, got one person there, and there's a point right in between. So we've got this person going out in this direction, and then we got the person going in the other direction. So they're both around that center point. So let me just figure that out. There we go. Okay. And the total, so that's our center point of rotation. And they're rotating, it doesn't really matter which way. It shows on the graph they're moving counterclockwise with some speed. And each section here, so the radius out to each person is 5 meters. And they say the people are, the mass is equal to 75 kilograms. So they're rotating around this center point. And it says moving circles a point halfway between them at a speed of 5 meters per second. So if you look at the actual speed of them in this direction, which will be tangential to the center point, that velocity is 5 meters per second. And it says treating the astronauts as particles. That just means that we're going to use the moment of inertia associated with them as just being this mass times the radius squared. Calculate the magnitude of the angular momentum and B, the rotational energy of the system. Okay, so the angular momentum is equal to omega times the moment of inertia. So all we have to do is calculate these two things. So the moment of inertia of this mass is going to be equal to the moment of inertia of a point mass is just mr squared. And our mass is 75 kilograms. Our radius is 5 meters. So if we multiply that out, we'll get 75 times 5 squared. 1,875 kilograms meters squared. And that's for one of them. So if we have both of them, the total, we'll call it total moment of inertia, is going to be 2 times that. 2 times 1,875 kilograms meters squared. And that's the moment of inertia around that center point. So we get 3,750 kilograms meters squared. So that's the moment of inertia. And the angular speed, all we have to do is there's the relationship between linear and rotational speed. V is equal to omega r. Therefore, omega is equal to V over r. So to calculate the rotational speed, we just take the velocity, which is given as 5 meters per second, divided by the radius, which is 5 meters. And so our rotational speed is just going to be 1 radian per second. The meters cancel out. You just have 1 over seconds, which, to put it in angular speed, is 1 radian per second. So the initial angular momentum is just the product of the angular speed, 1 radian per second, times the moment of inertia, which is 3,750 kilogram meter squared. So that's pretty easy. It's 3,750. The units are kilogram meter squared per second, which is the same as a joule second from a previous problem. And the kinetic energy of a rotating system is 1/2 I omega squared. Instead of 1/2 mv squared, it's 1/2 I omega squared. And there's no linear movement of this center of rotation. So this is all rotational kinetic energy. So we can just plug that in there. 1/2 I, which is 3,750 kilogram meter squared, times omega, which is 1 radian per second quantity squared. And so we just take half of that, half of 3,750, because 1 squared is 1. So we get 1,875 kilogram meter squared per second squared, which a kilogram meter per second squared is a joule. It's energy, 1,875 joules. Okay, so that's the energy, kinetic energy, angular momentum. Okay, then the second part says, by pulling on the rope, the astronauts shorten the distance between them to 5 meters. So our radius will become 2.5 meters. What is the new angular momentum of the system? What are the new speeds? What is the new rotational energy of the system? How much work is done by the astronauts in shortening the rope? Okay, so let's look at each one of these separately. Well, because what's going to happen is you're going to have these astronauts that are going to be pulling on the rope, but that force is internal to their system, so there's no external work done. So the external work is 0. If the external work is 0, and in that case, for part C, the final angular momentum is going to be the same as the initial angular momentum from conservation of angular momentum. So L final, this is after they've shortened the rope, is still 3,750. It's just like when I did the demo in class where I spun around and then I brought my arms into my body. I was doing work to make that happen. But it was internally to me. It wasn't external. Nobody was pushing me. So that the total angular momentum stayed the same. Okay, part 3. What are the new speeds? Well, the angular momentums are the same, but what happens is I change the moment of inertia by changing the distances. So what we're going to do is we know that the final moment of inertia times the final rotational speed is equal to the initial moment of inertia times the initial rotational speed. And we've already calculated that. That's 3,750. And we know this is also 3,750. What we're going to do is we're going to calculate a new moment of inertia when they've moved in. So what changes is the radius. So the moment of inertia for each person is still going to be the same. It's going to be the same mass, which is 75 kilograms. But the radius now, instead of being 5 meters, is going to be 2.5 meters because they shortened the rope by a total of in half. So it was 10-meter long rope, so it becomes 5 meters, and half of 5 meters is 2.5 meters. So we take 75 times 2.5 squared. So we get 469 kilogram meter squared. That's 1/4 because you take half of the distance and you square it and you get 1/4. So the moment of inertia for each individual body is 1/4, and so the final moment of inertia is equal to twice this because there are 2 people. So 469 times 2 is 938 kilogram meters squared. If we multiply that by 2, we should get 1875. And if we multiply by 2 again, we'll get 3750. So I didn't make any mistakes there. So that's the final moment of inertia. Therefore, the final angular speed is going to be equal to the initial moment of inertia times initial rotational speed divided by the final rotational speed. Pardon me. Final moment of inertia. And, you know, we can plug the numbers in. So the final rotational speed is, what do we got here? The moment of inertia was, let's go back to the original page. The initial moment of inertia was 3750. 3750 divided by the final moment of inertia, which is 938. This is going to be 4. And we multiply by the initial rotational speed, which was 1 radian per second. So we end up going 4 radians per second is the final rotational speed. And we can calculate the final velocities just by taking the rotational speed times the radius. And so we have 4 radians per second times the radius. The radius is only 2.5 meters, not 5 meters. So 4 times 2.5 is 10 meters per second. So what happens is the rotational speed increases by a factor of 4. The linear speed increases by a factor of 2. We go from 5 meters per second to 10 meters per second. Okay, so that was part D. What is the new rotational energy of the system? We use the same relationship here. Kinetic energy is the rotational energy. So we'll have a new I, which will be 938, and we'll have the new omega, which will be 4 radians per second squared. So let's add page. So the final rotational kinetic energy is 1/2 I final omega final squared. So we have 1/2. The final moment of inertia is 938 kilograms meters squared times omega, which is 4 radians per second, and we square that. So we get 0.5 times 938 times 4 squared, and we get 7,500. And this is units of kilograms meters squared per second squared, which is 7,500 joules. So that's the kinetic energy final. How does that compare with our initial kinetic energy? 1,875. So that was 1,875 joules. And we finally end up with 7,500. Did I multiply by 0.5? Yeah, I did. Okay, so make sure everything's right here. Okay, so I did everything right. I just want to make sure before I went any further. So you can see our kinetic energy has increased. So what's going on here? We start off them rotating with a kinetic energy of 1,875. They end up with a kinetic energy of 7,500. So we have constant angular momentum based on conservation of angular momentum, but somehow the energy is increasing, and that's where F comes into how much work is done by the astronauts in shortening the rope. So conservation of energy would say that the work is equal to the change in kinetic energy plus the change in potential energy. There's no change in potential energy. So all the work done, and this is work done internally, results in this change in kinetic energy. So the work is going to be equal to the final kinetic energy minus the initial kinetic energy. So we have a final kinetic energy of 7,500 joules. We have an initial kinetic energy of 1,875 joules. So the difference between those two, 7,500 minus 1,875, oops, I multiplied 1,875 is 5,625 joules. So that's the amount of work done. So when those guys are pulling the rope, when they're pulling themselves towards each other, they are doing work. They're having to use energy from their bodies to pull that rope closer. And that energy that they use to pull the rope closer together has to go somewhere. And that, where it goes, is it goes into the kinetic energy of the rotation. So likewise, when they're going out the other direction, say they were close together and they went further away, what happens there is, as you would still conserve angular momentum, but in this case, the work would be the opposite. Now, the thing is that we can't recover that work, so that there would be friction loss as they move to the outside. You know, they would, as they're moving along, their gloves would be rubbing against the rope, and that would cause heat, and that would result in, that would be where the energy went to. It would be you couldn't get it back. In this case, they're burning calories in their bodies, which they can't get back either. So in both cases, the work is not recoverable. But anyway, that's what goes on here. So let's kind of review what happened. We have these two guys rotating around this center point. We can calculate an initial angular momentum associated with that. The angular momentum is the product of the angular speed times the moment of inertia. So we calculated the moment of inertia by looking at the moment of inertia of each person. So it was the mass of the person times the radius from the point of rotation. So we get 1875 kilograms per meter squared for each person. So if you multiply that by 2, you get the total moment of inertia, total moment of inertia of this system of 3750. We calculated the rotational speed by using the relationship between linear and rotational speed, this relationship, and solve for omega. So omega was v over r. So we took the velocity that was given in the problem divided by the radius, gave us the rotational speed in radians per second. So knowing omega and knowing the moment of inertia, we could calculate the angular momentum. And we can also calculate the initial kinetic energy associated with this setup. It's 1/2 the moment of inertia times the angular speed squared. So we just plugged the numbers in, we got 1875 joules. Now, the two guys pulled on the rope, shortened the rope to half the distance, so this radius went from 5 meters to 2.5 meters. Because there was no external work added to the system, then the angular momentum had to stay the same. So to calculate the new angular momentum, we know it's the same as the old angular momentum. Then we can use conservation of angular momentum to calculate the final rotational speed by calculating the final moment of inertia. The moment of inertia changes because the radius becomes half of the original radius. So the moment of inertia is reduced by a factor of 4 because the radius is reduced by a factor of 2, which when squared becomes 4. So this is the moment of inertia associated with each body. So we multiply by 2 to get the total moment of inertia. This is 1/4 the initial moment of inertia. And we can solve for the final rotational speed by taking this relationship. And we find out the rotational speed increases by a factor of 4, from 1 radian per second to 4 radians per second. And then we can calculate the linear speed by multiplying the rotational speed by the radius. So the rotational speed increased by 4, but the radius decreased by 2, so the linear speed increased by a factor of 2. To calculate the final kinetic energy, we just use the relationship for kinetic energy for a rotating system, which is 1/2 I omega squared. So we take the final moment of inertia times the final angular speed, and we get 7,500 kilograms meters per second squared, which is a joule. And we compare that with the initial kinetic energy, which is 1,875 joules. So where did this energy come from? It came from the muscles in the guys pulling on the rope. And we can calculate what the work done by the people when they're shortening the rope. Conservation of energy says that the work is equal to the change in kinetic energy plus the change in potential energy. There's no change in potential energy. So the only change is going to be change in kinetic energy. So you take the final kinetic energy minus the initial kinetic energy, and you get the work is 5,625 joules. And that's the answer. Okay, we're doing 79, Chapter 8, page 266. It's funny, it's a blue problem, but it's really not that hard. So let's read the problem. In exercise physiology studies, it is sometimes important to determine the location of a person's center of gravity. This can be done with the arrangement shown in figure 879. A light plank rests on two scales that read 380 newtons and 320 newtons. The scales are separated by a distance of 2 meters. How far from the woman's feet is her center of gravity? So what we have is this, we'll assume that she's 2 meters tall. So let's just draw the plank, and then we're going to have two forces acting up, holding up, and that's what the scales are reading. And the distance between the two scales is 2 meters, which we are assuming also is the distance between her head and her foot. And what we find out is that if we look at the left-hand scale, it reads 380 newtons, and the right-hand scale reads 320 newtons. So we'll call this F sub L, and we'll call this F sub G, or F sub R for right, left and right. So you have this person laying on here, which will represent her by a rectangle. So here she is laying on here. And her center of gravity is where we can say all of her weight is concentrated and give the same result as if this weight were distributed evenly. And because this is higher than that, it's going to be a little bit off center. If she had her center of gravity right in the middle of her body, then the position would be the center of gravity would be right in the middle, but like most people, they're top heavy because their legs are not as massive as their chest. So anyway, what we're going to do is we're going to call this distance here from her center of gravity to the right hand support X. And then we're going to sum the forces around this part, and then we'll be able to solve for X. So this, if we use this as our center of rotation right here, this force contributes no torque. This one creates a counterclockwise torque, which is positive, and this one creates a clockwise torque. So all we have to do is we just have to sum the torques around, we'll call this point O. Because they're in equilibrium, it's equal to 0. So we have this torque, which is going to be positive, and what is her weight? Well, we know it's going to be the sum of these two. Okay, what's pushing up? And it says it's a light plank. That's why we have to assume that the plank weight is negligible compared to their weight. So we know that the magnitude of this force from the sum of the forces in the y direction is going to be 700 newtons. So that's her mass, or her weight. Okay, so what we get is we get 700 newtons times the distance x, which is positive, and then we subtract off this, which is going to create a negative torque of 380 newtons times the total distance, which is 2 meters. and therefore x is just equal to 380 times 2 divided by 700. If I plug that in the calculator, 380 times 2 divided by 700, and we get x is equal to 1.08 meters. So it is slightly, if we got 1 meter, then it would be exactly in the middle, but it's slightly larger than 1 meter, and therefore it is 1.08 meters. So that's pretty easy, wasn't it? And it's just the answer, and it's 1.09 meters. I just rounded off incorrectly, so if you wonder why mine wasn't exactly equal to the back of the book, it's 1.0857, which rounds up to 1.09 meters.
Okay. So let's just put these. Let's put it in here. So okay, this is problem number 83. Apparently, I forgot to do. So this is the initial omega is 0. So the change in kinetic energy is going to be it's a trebuchet, and so we'll have basically what's going to happen here is we are going to convert potential energy into kinetic energy. Well, kinetic energy is one half. Two components of kinetic energy. There's going to be total linear squared. Well, yeah, we don't have 0 because twice into account 0. So there's going to be linear kinetic energy, but we're going to the center of mass of this thing changes potential energy, which is negative 78. Basically, it's going to be conservation of energy, and that equals 0. And conservation of energy, because, so you can see what we can do is we can solve for omega squared. It says the maximum speed, that means there's no work times negative 78 externally on this thing. Well, work internally. The other side is going to be changing negatives. Again, is negative potential energy to kinetic energy. Well, so we're going to draw this out, and then we divide by. Either way, here's our initial trebuchet, 8.9. So we're going to rotate around this point, and we're going to have this mass here, which is total 60 kilograms, 2.157. Let's call that M kilograms per meter. Small mass out here, which omega squared is equal to 2 times 78, and it has a mass of 0.120 kilograms, 2.157, which defines which is 72 in a rotation to this distance per meters there. Now, let's just take the units out. The joule is a Newton meter. So it says that kilograms per meter squared. The Newton is a kilogram meter per second. So squared is 3 meters. Okay. Then we have a meter divided by kilogram meter squared. Stiff rod, let's cancel out. Okay, so the whole thing's 3 meters. So with that, and you end up with one other side squared, which is the same as 3 meters squared. So I need to make sure I do that right. Radians per second squared. And it says that you can turn on a friction horizontal axis perpendicular to the rod, and I get omega 14 centimeters from the particle of a larger mass. So 6 is here. Second. So that's the rotational speed. It's not drawn to scale. And then you calculate the velocity 14 centimeters. So this is going to be 0.14 meters. So omega divided by 100 is 8. So ultimately, this number per second, this distance is here. 2.86 is the difference between those two, which is this is the radius 2.86 meters. So 2.86 plus 0.14 is 3. Okay, so what's going to happen here? You said that the change in kinetic energy plus the change in potential energy 6 times 2.86 0. There's no springs, there's no external work done. It's rotating around 24.5 meters. And so we're going to have a decrease in potential energy associated with this thing swinging down. I'm just going to pause for a second. Increase in potential energy associated with this thing. See if there's anything So let's do that separately. So delta potential energy is going to be, okay, so that's the correct answer. Everything's fine. So let me just explain again what we did here. And the potential energy is, because we were rotating these two things about this axle, GH, and the axle does not move, then the center of rotation we choose is not, does not move in this case. So we don't have to worry about these linear, even though the center of mass is really over here. We're not talking about the center of mass. We're just talking about the center of rotation. If you pick this as your point that you do the energy about, the increase of potential energy, then we have a decrease of potential velocity associated with that. So that's why we picked this point. So the velocity, the linear velocity is 0. And therefore we can just treat this as rotating object squared. And it decreases. So what we said was that the decrease in potential energy of this meters and the increase in potential energy of that result is not negative, then we're in trouble. So here this is a smaller distance. Decrease in potential energy sufficient result so that an increase decrease in potential energy is much higher than 1/2's increase in potential energy into the negative change in potential energy. You decrease potential energy, therefore it has to go into something. And if all of that goes into kinetic energy, then you get the maximum speed. And correctly, we said that the linear kinetic energy was this form, so that reminded me that the rotational kinetic energy is 1/2 I omega squared. There's the pin here, I for n, and omega for negative 78.9. So we take the total moment of inertia of the two elements, which we consider to be point masses, which is m r squared, and kinetic potential energy is in joules. So we have these units of 6 squared times mass and 0.14 squared times mass. What kind of is the total moment of inertia? And let's just look, but it's 60 times change in kinetic energy. Well, we have, so remember it is linear kinetic energy is 1/2. And so each one of those contributes, in terms of rotational system, it's 1/2 inertia I of omega squared. Because we're squaring the, what we're going to do is we're going to solve for omega. Actually, by doing this, that contributes first need to calculate less than that, but they're very close to each other, about half. So we actually have 2 point masses to each one. We have I total. So that was a total moment of inertia. We said that conservation energy I1, change in kinetic energy plus change in potential energy, moment of inertia of each part is equal to 0. If there's no external point mass, it's just m squared. No forces acting on this externally. M1 is 6m, that's 0 kilograms. So times change in kinetic energy is the final kinetic energy minus the initial kinetic energy squared. Initial kinetic energy is 0 because the other one is 0.120. So it's just the final kinetic energy. Kilograms times I omega squared. 2.8. We already calculated our change of potential energy squared. Negative. Our total moment of inertia solved for omega squared is 0.14. Will come over here as positive. Plus, it's probably better just to make this one positive. So you move that to the right-hand side, it becomes positive 0.12, but multiply by 2, divided by 0.12 total kilograms, that's right, of inertia, 12 kilograms. So what we have here, let me just write that, times omega is equal to squared. Basically, delta potential energy, so we got a total moment of inertia, or 2 times the potential energy change equal to 2.1 inertia, 7 square of the rotational meters squared. Plug the numbers in, we get that. We take the square root of that. So now we should be able to figure out what omega is. And once we know omega, we can use the velocities. Omega times r should be to solve for the velocity speeds, and we get the final answer. Okay, just hold on just a second. Just make sure I was recording. Okay. So let's just put these. Let's put it in here. So, change in kinetic energy, delta kinetic energy, and so this is the initial omega is 0. So the change in kinetic energy is going to be the final minus the initial. So we'll have delta kinetic energy plus delta potential energy equals 0. Delta kinetic energy is 1/2 I total times omega squared minus 0 because omega is 0, 0, the initial omega, plus the change in potential energy, which is negative 78.96 joules, and that equals 0. So you can see what we can do is we can solve for omega squared. It's going to be equal to 2 times negative 78. Well, when we move this to the other side, it's going to be negative, so we'll have a negative times a negative. Well, we moved it to the other side, it's negative, and then we divide by, either way, it comes out to be positive, so 78.96 joules divided by I total, which is 2.157 kilograms meters squared. So we get omega squared is equal to 2 times 78.96 divided by 2.157, which is 72.2 radians per second. Now, let's just take the units out. A joule is a Newton meter divided by kilograms meters squared. But a Newton is a kilogram meter per second squared. And then we have a meter divided by kilogram meter squared. So those cancel out. These two cancel with that. And you end up with 1/second squared, which is the same as radians per second squared. So I need to make sure I do that right. Radians per second squared. Radians squared per second squared. Okay, so you take the square root of that, 0.5, and I get omega final is 8.56 radians per second. So that's the rotational speed. And then you calculate the velocity by taking omega times r. So omega is 8.56 radians per second. R is 2.86, I think. So this is the radius, 2.86. So that's 2.86 meters. So we get 8.56 times 2.86 is 24.5, which is the right answer. 24.5 meters per second. Yeah, I'm just going to pause for a second. I know this is the answer. I'm just going to look at the other solution, see if there's anything I need to tell you. Okay, so that's the correct answer. Everything's fine. So let me just explain again what we did here. Because we were rotating these two things about this axle, and the axle does not move, then the center of rotation that we choose does not move in this case. So we don't have to worry about the linear, even though the center of mass is really over here, and we're not talking about the center of mass, we're just talking about the center of rotation. If you pick this as your point that you do the energy about, that point actually would move, and you'd have a velocity associated with that. So that's why we picked this point. So the velocity, the linear velocity is 0, and therefore we can just treat this as a rotating object. So what we said was that the decrease in potential energy of this and the increase in potential energy of that resulted in a net change in potential energy. So even though this is a smaller distance, the mass is sufficient so that this decrease in potential energy is much higher than this increase in potential energy. So you end up with a negative change in potential energy. You decrease potential energy, therefore it has to go into something. And if all of that goes into kinetic energy, then you get the maximum speed. So we said that the linear kinetic energy was this form, so that reminded me that the rotational kinetic energy is 1/2 I omega squared, using I for m and omega for v, besides just looking at it in the book. So we take the total moment of inertia of the two elements, which we consider to be point masses, which is mr squared plus mr squared of each one. So we had 2.86 squared times the mass and 0.14 squared times the mass. That gives the total moment of inertia. And let's just look, but it's 60 times 0.14 squared is 1.176. So each one of those contributes about the same amount to the moment of inertia of the system, because we're squaring the second. Actually, this contributes a little less than that, but they're pretty close to each other. About half of the moment of inertia is due to each one of those. So that was the total moment of inertia. And we said that conservation energy says the change in kinetic energy plus change in potential energy is equal to 0 if there's no external work done. And because there's no forces acting on this externally, then that's 0. So change in kinetic energy is the final kinetic energy minus the initial kinetic energy. The initial kinetic energy is 0 because these are not moving. So it's just the final kinetic energy, which is 1/2 I omega squared. And we already calculated our change in potential energy, which is negative. So if we solve for omega squared, this will come over here as positive. It'd probably be better just to make those both positive. So you move that to the right-hand side, it becomes positive. Multiply by 2, divided by the total moment of inertia. So what we have here, let me just write that. Omega is equal to basically delta potential energy divided by, or 2 times the potential energy change divided by the total moment of inertia. That gives you the square of the rotational speed. So we plug the numbers in, we get that. We take the square root of that, and we get 8.56 radians per second.